Hopefully you remember from algebra that if you have a function like, oh, I'm going to just make one up here, y equals x squared plus 2, I can find its inverse by switching the x and the y, then solving for y. Let's subtract 2 from both sides. Now I'm going to rewrite it with the y stuff on the left-hand side and take the square root. Now, plus or minus, because I'm dealing with this algebraically at first, I may have to consider restricting my domain, but for right now, I'm going to leave it as plus or minus. Now, the nice thing about this is that when you compose a function and its inverse, you get a very predictable answer, because what a function does to x, the inverse function undoes. That's what inverses do. So I'm going to rename these. I'm going to name this f of x. That means that this one is called f inverse of x. And I'm going to take the composition of f with f inverse of x. That means take the function f, which is x squared plus 2, and into it put f inverse. So wherever you see an x, put an f inverse. And then I know what f inverse is because I just found it. It's plus or minus the square root of x minus 2. But because the original function's x input value was squared, I'm going to square that, and then I'm going to add 2. And then I'm going to simplify. When you square a square root, first of all, when you square anything, it's positive, so I don't need to worry about this negative sign anymore. And when you square a square root, the square and the square root cancel each other out, so I've got just x minus 2. Where did my 2 go? Over here. And then I have plus 2, so I'm left with x. And that's always going to happen when you compose a function with its inverse. Let's try it the other way around. F inverse composed with f means take f inverse, which in this case is the square root of x minus 2. And everywhere you see an x, put an f. Put the function f. So that's going to be plus or minus the square root of f of x minus 2. Well, we know what f of x is. We were given that function to start with. It's x squared plus 2. And then I have this minus 2 to bring down as well. When I simplify that, I get x squared plus 2 minus 2. Well, and the square root of x squared is just x. Here I have plus or minus x, so that could be a little tricky. But the point that I want to make with this is that I still just got x. And that's the easy answer, right? If I do this with trigonometric functions, as we've already seen in the previous video, the answer should just be whatever the input was becomes the output. Whatever the output was becomes the input, right? Let me show you what I mean. When we were dealing with that x squared plus 2 function, we were actually able to find another function in x and y that was the inverse. We can't really do that with sine inverse because it's just sine inverse. But I can plug a value in for x here, figure out what the sign of that value is, and then find the inverse of that. Equally, I could find the sine inverse of some ratio, that would be an angle, and then take the sine of that angle. No matter what value I plug in for x here, anything between 0 and 2 pi, something bigger than 2 pi, because I can find its coterminal angle, or even something smaller than 0, because again, I can find a coterminal angle and I'll be able to find the sine of the original angle based on the sine of the coterminal angle. I can place the too big or too small angle back into the 0 to 2 pi region. So if I can find the sine of an angle, I can find the inverse sine of that ratio. That would be a ratio, right? Except as in the previous video where the ratio was the angle was outside the negative pi over 2 to pi over 2 region. So there will be times when we can't do this directly, but we can always find the sine inverse of the sine of an angle. So to give you a simple example, let's say that the angle is pi over 6, why not? I can do this part very easily. The sine of pi over 6 is a half. So that means I can replace the sine of pi over 6 with 1/2. What this expression is asking me is, what is the angle remember the sine inverse has an input of a ratio and the output of an angle. What is the angle whose sine is 1/2? Well, that's pi over 6, right? So in the case that the angle we start with, this one right here, is between negative pi over 2 and pi over 2, the answer is just that angle. The sine inverse of the sine of the angle is just the angle. Just as in algebra, when we were able to say that the function evaluated at its inverse is just x, right? The input is the answer if you're composing the function with its inverse. And that's what we're doing here, we're composing a function with its inverse. This is in a different order, but we found on the previous screen that whether the inverse is on the inside or the outside, the composition of a function with its inverse always produces just the argument as its answer. And so here the argument is pi over 6. So if the angle we're given to start with is between negative pi over 2 and pi over 2, then that's the answer. If it's not, it's a slightly different story. This is related to the problem we did on the previous in the previous video. When I asked you to find the sine of 4 pi over 3, we were able to do that because the sine of 4 pi over 3 is the same as the sine of the reference angle pi over 3. Now go check whether it's positive or negative. We were able to determine that the sine of 4 pi over 3 was the square root of 3 over 2, because the sine of the reference angle pi over 3 was root 3 over 2. But because 4 pi over 3 is in quadrant 3, the answer is negative. In a separate problem, then I asked you to try to find the sine inverse of negative root 3 over 2. And the answer, we said, felt like it should be 4 pi over 3. But 4 pi over 3 is not between negative pi over 2 and positive pi over 2. So we had to work our way around that and figure out that the inverse sine of negative 3 pi over 2 is negative pi over 3. So it's not exactly the input that we were expecting. The answer 4 pi over 3 here would be wrong, because the answer to this question, whose angle has a sine of negative 3 pi over 2, can't be outside quadrant 4, below 0, negative pi over 2, and quadrant 1 up to pi over 2. It can't be outside that region. 4 pi over 3 is outside that region. This cannot be the answer. On the other hand, we can have easy and hard versions of this version of the problem as well. We can have questions like find the sine of the sine inverse of a half. Well, we know that the sine inverse of a half is pi over 6. And we also know that the sine of pi over 6 is a half. So there you have it. That's it. We're done. What if I ask you to find the sine of the sine inverse of 2? Now, what this inside part of this problem is asking me is, remember this is a sine inverse, so instead of plugging in an angle and getting out a ratio, I'm plugging in a ratio. So let me remind you what the graph of the sine function looks like. This is just a rough sketch. But by way of reminder, it only goes up to 1 and down to -1. Now, along the x-axis here, we have angles, pi over 2, pi, 3 pi over 2, 2 pi, and so on. We can go in both directions. So because this is the sine inverse, I'm asking you, what is the angle that outputs a ratio of 2? Now, a ratio of 2 can be thought of as 2 over 1. That's still a ratio. That works. The thing that doesn't work is the fact that there is no angle that spits out a value of 2. It only goes up to 1. So the answer here is there is no such angle. We tend to write DNE for that. Does not exist. I don't know that that's necessarily mathematically generally considered an appropriate way to express the idea that the solution does not exist. One way to do so would be to give the empty set. Another way of writing the empty set is just that. But because of the software that we use to do our check your understanding problems and also the basic skills test, that software, when an answer doesn't exist, this is how it wants you to input that information. So DNE means the solution you are seeking does not exist. And that's what happens here. Sine inverse of 2 never exists. There is no angle here for which the sine value output is 2. Never. So there can be tricks in these problems. The sine inverse of too big of an angle, for example, or the sine of a big angle that takes the inverse and means you have to go find a smaller angle or a different angle. So you have to be careful with these. But this is what is meant by working with composite functions with inverses involved. Now, we had talked about this problem, this sine inverse of a sine of an angle that was really too big. We talked about that problem in the previous video. I've reintroduced it here using composite notation, so now it's in a little bit different form. So we've really kind of addressed the situation here, but there is one more sort of combination of things that you might see. So I'm going to erase the screen and write a slightly different problem. Maybe I'll only erase half of it, so we have maybe this half to refer back to. I'll erase this half so we can use this other side as a comparison. All right, here we have another composition, but this time instead of having a sine inverse of a sine or a sine of a sine inverse, I have two different kinds of functions. One's a sine and one's a tangent. One of these is an inverse. You might also see, for example, cosine inverse of the sine of a value. Or you might see the tangent of the cosine inverse of a value. All right, so the sine can be either the inverse can either be inside or outside, and these can be made up of sines, cosines, tangents, cotangents, secants, and cosecants. Again, because we haven't really worked in the videos with much other than sine, and earlier on we learned some values of cosine, a few of tangent as well. I'm going to stick with familiar values as much as possible for the first example, and then for the other examples I may have to stretch a little bit, but I'll explain it as I go along. Now this is another example of, can we find this value? And if we can, then can we find the angle whose sine is the result, right? So let's start with the inside. What is the tangent of pi over 4? I hope you know by now that that's 1, right? Pi over 4 is the 45-degree angle. So this angle and this angle are the same size. And I want to know what the coordinates of that point are. This has a radius of 1. And the coordinates of that point are 1 over the square root of 2 and 1 over the square root of 2. X and Y are the same. That's cosine, and that's sine. And tangent is sine over cosine. And anytime you take a number and divide it by itself, you're going to get 1. So the tangent of pi over 4 is the sine of pi over 4, which is 1 over root 2, divided by the cosine of pi over 4, which is also 1 over root 2. So therefore, the tangent of pi over 4 is 1. So what I've done is started with the inside piece here and just evaluated it. Go figure out what that is. It's 1. That's pretty easy. Now if you think about the graph of sine again, remember that it only goes up to 1 and down to -1. You want to ask yourself, whose angle produces a sine of 1? What's the name of the angle that produces a sine of 1? All right, so we want to know which input value here produces a 1. Well, there's one there, and there's one there, and there's one back here, and in fact, there's an infinite number of them. However, we are restricted to working between negative pi and pi, negative pi over 2 rather, and pi over 2, because we're working with sine inverse here. We're restricted to this part of the graph, right? This part of the domain. So where in this stretch is the y value 1? It's right here. What's the x value that gives you that? And it's pi over 2. Okay, I'm going to move things around just a little bit here, and we're going to do another example, because that one was pretty straightforward. It was easy to find the tangent of pi over 4. We found the value here of 1 gets output within the range of values that we need, negative pi over 2 to pi over 2, so we just put in the answer here. But what happens if you end up with something like this? Here we're asked, first of all, to find, I'm going to make my highlighter just a little bit bigger, to find the value of the cosine of 5 pi over 6. We're not explicitly asked to find that first, but that's just what makes sense. We need a value to take the sine inverse of, and that value has to be in here. And right now it's not in a convenient form. Let me move this down a little bit. So we need to put it in a more convenient form. We need to figure out what this value is, what this cosine of 5 pi over 6 is, and then we can find out whether or not taking the sine inverse of that is possible and what the value is. So let's go to the unit circle. This may not end up staying on the screen, but we'll see. Whenever I see like a denominator, I'm not too sure like how many, where is this angle, right? So I'm going to look to the denominator. I'm going to say, well, where is 6 pi over 6, right? Because 6 pi over 6 is equal to pi, right? This is easy division to do. Where is that? Pi is 180 degrees. So I'm looking at this angle right here. But I was asked for 5 pi over 6. So I want to go all the way over to 6 pi over 6 and then back up by 1 pi over 6. So the angle I'm looking for, or trying to work with here, is this one here. This is 5 pi over 6. To find its cosine, though, all I really need to do is to work with the reference angle, which is pi over 6. What is the cosine of pi over 6? Let me rewrite this problem first of all. The sine inverse of, I'm going to put a value in here that's equivalent to the cosine of 5 pi over 6. What is the cosine of pi over 6? Well, that's root 3 over 2. Okay. Now, is it positive or negative? Well, it's in quadrant 2, but I'm dealing with cosine here. All students take calculus. Cosine is only positive here. Well, and in quadrant 1, because everything's positive in quadrant 1. Quadrant 1 and quadrant 4, all students take calculus. C is in quadrant 4, so cosine is positive down here. That means it's negative over here. Cosine is negative in this quadrant, so therefore, this is going to be negative, the square root of 3 over 2. So now what we need to do is find an angle whose sine is negative square root of 3 over 2. Well, it has to be one of the following. Because the sine of an angle is root 3 over 2, when the reference angle is pi over 3, it's either going to be pi over 3, my pen's not working, pi over 3, or 2 pi over 3, or 4 pi over 3, that one's not quite in the right place, 4 pi over 3, or 5 pi over 3. There's pi over 3, 2 pi over 3. This would be 3 pi over 3 right here, but that's pi. And it doesn't have a reference angle of pi over 3. There's 5 pi over 3, 4 pi over 3, and there is 5 pi over 3. So those are the 4 angles that are candidates for being an answer to this problem here. But the problem is we're dealing with sine inverse. So we're restricted to working in this region here. Quadrant 4 and quadrant 1. So which one is it? Well, these are the places we can play with sine inverse, but the answer, which angle has a sine of negative 3/2, the answer has to be negative. All students take calculus. All trig functions are positive in quadrant 1, so it must be in quadrant 4. And in fact, all students, right? Sine is positive in quadrant 2, but not in quadrant 3 or quadrant 4. So our answer has to be in quadrant 4. Let me redraw this. So there's our answer. There's the angle we need to work with. But again, remember that the answer has to be between negative pi over 2 and pi over 2. And not between 0 and 2 pi. This angle can be thought of as either, let's see, we're in pi over 3s. So that's 3 pi over 3, 4 pi over 3. This is 5 pi over 3. 5 pi over 3. And that's between 0 and 2 pi. The other way we could think of it is as 0 minus the reference angle, which is pi over 3. So negative pi over 3. And only one of these is between negative pi over 2 and pi over 2. And that's this one right here. So that's our answer. negative pi over 3. My main reason for going to the length of detail that I did with this particular example is that it's a pretty sticky place for a lot of students. It's really easy just to say, find the cosine of 5 pi over 6 and then take the inverse sine of that number. But that number may not be that may not give you an angle in the right place. So you have to be careful to find the right one. That's the last video for this section, and in fact for this chapter. Better still, for this module. This is the end of module 1. So this is the last video you'll see with new content before you're going to take a basic skills test and a challenge set. Don't forget that there's quite a bit we haven't covered in the videos because there wasn't really time, and we needed something to do in class as well, right? So we learned a few things in the videos, and then we expanded those and extended them in class. So make sure you use your notes from class as well as your notes from the videos while you're studying for either the basic skills test or working on the challenge set. Other than that, I'll see you in the next video at the beginning of the next module.